Thanks all, and good morning or afternoon or evening or wherever, whatever it is, wherever you are. And I'm really looking forward to taking on the role of actor postdoc at McGill, to meeting more of you and to hopefully collaborating as well. And so I'm excited for this opportunity to kind of introduce myself by sharing some of my dissertation work. So my dissertation is titled Empirical Approaches to Timbre Semantics as a Foundation for Musical Analysis, and that's available pre-publication form on my ResearchGate account. And in that dissertation, I report the results of several studies on timbre semantics. In the last chapter, I develop a computational method for analysis for large ensemble music that uses the model that I derived empirically. So my plan today is to focus on 3 of the chapters of the dissertation as they relate to that Timbre Qualia model. Thus the title for this presentation, which is a model of the cognitive linguistics of Timbre Qualia. So the first topic I'm going to focus on is my model building process. I used content analysis of interviews with musicians and principal component analyses of a subsequent rating task to construct a 20-dimensional cognitive linguistic model. And next I'm going to describe my Timbre Trait Profiles. So these are kind of cognitive linguistic character sketches of musical instruments that are built from the results of a rating task that used the 20-dimensional model. And then finally, I'll talk about some initial work I did on register and dynamics, again, using this model. So the article that describes the model building process is a collaboration with David Huron, and it's recently become available in online first format in psychomusicology. And again, the pre-publication version is available on my ResearchGate if you don't have access to the journal. So our goal in building this model was to generate a tool that would be useful in musical analysis to address questions of timbre and orchestration. So we were interested especially in the phenomenal character of instrumental timbre, thus our focus on Timbre Qualia rather than simply timbre. And a lot of great work has been done already in semantics, and several previous models have suggested between usually 3 and 5 dimensions. The ways in which our work differs from this previous research includes this broader focus on Timbre Qualia, the derivation of our terminology from musicians, from the interviews with the participants, and our intention for the use of this model in musical analysis. So another important point is that we came to our model building process with the consideration that for music theorists, a model that would be really useful for musical analysis might actually not be the most parsimonious model, which has been traditionally what we look for. So this kind of idea is key in understanding the model building, decision-making process, especially towards the end. So the first stage of the process was a series of interviews, so with professional musicians, and I asked them to describe the sounds of 20 musical instruments. I first asked participants to imagine the sounds of the instruments and then to describe what they're hearing. So the decision to use imagined rather than recording stimuli was based on a number of factors, all of which are explained in the article, but basically a general motivation to characterize a prototypical sound of an instrument rather than any specific recorded instantiation. I also collected vividness and familiarity ratings from the participants about their imagined sounds. I'm just going to take a moment here to note that the current studies were constrained to Western classical instruments and were conducted in English, though in the future I hope to be applying parallel methodologies to other genres and cultures and languages. So if that's something you are interested in collaborating on, please let me know. So the responses from the interviews were super colorful, super creative, really fun. And ultimately, for the purposes of the model, we ended up reducing this to kind of adjectival descriptions. But I also produced a second analysis of these interview transcripts that focuses on response strategy. And that's what I'll be sharing during the Timbre Semantics work group session on Thursday. But for now, I will focus on the model building process. So after parsing the interviews into about 4,800 component ideas and cleaning the data. David and I each did an individual pile sort on the ideas that were occurring more than once in the interviews, which was about 500 terms. And we reconciled our results together to come up with this preliminary model of about 77 categories. And these 77 categories became the foundation for a rating task. So in this rating task, 460 musicians participated. 60 of these were Ohio State students, and the other 400 were recruited online via Qualtrics. The 20 instruments, these were the same instruments that were described in the interviews, were rated on that initial 77 category model. And we again collected ratings of familiarity and vividness, and then subjected these rating results to principal component analysis. The interpretation began in a pretty traditional way with eigenvalues and U-plots, but we quickly realized that these kind of typical rule of thumb approaches, which are just that, they're rule of thumb and they are somewhat arbitrary, and they're also aimed at finding the most parsimonious model, which wasn't necessarily our aim, wasn't quite getting us the model we thought would be useful for music theory. So what we ended up doing was looking at a really wide range of models and suggested by different principal component analyses. And we used further participant input via a couple more studies to derive a final model of 20 dimensions. So here they are. Each dimension contains a set of linguistic terms. And the full dimension is on the right column. The shorthand label that we've offered is on the left-hand column. It's just easier to say. So I think it's worth it to give a quick read through to the model dimensions. So there's rumbling low, soft singing, watery fluid, direct loud, nasal reedy, shrill noisy, percussive, pure clear, brassy metallic, raspy grainy, ringing long decay, sparkling brilliant, airy breathy, resonant vibrant, hollow, woody, muted veiled, sustained even, open, and focused compact. So in the article, we offer some speculations and hypotheses about the potential origins of each of the dimensions, which we are proposing, hopefully, to be tested by future research. We find that while a lot of the initial language that people used in the interviews was related to historical or cultural factors, and a lot of that was highly metaphorical or poetic, in the final model, when the dimensions boiled down to what are the most intersubjectively reliable descriptors, essentially, that those terms actually seem to be driven by the simple presence of discriminable acoustic features. So we consider that this might suggest that there's a generalized learning account of linguistic timbral categories. Okay, the next step in my research was to use this 20-dimensional model in a rating task to generate what I call Timbre Trait Profiles, which are these kind of cognitive linguistic character sketches. So you could think about these as kind of personality descriptors or personality tests for the instruments. And just like with personality descriptions, you could think that maybe I'm accurately described as having a bubbly personality, for example. But that's not necessarily implying that I'm going to be bubbly in every single circumstance or context. But that at the same time doesn't nullify the usefulness of the descriptor bubbly and maybe predicting what kind of behavior I might have in different kinds of contexts, or knowing what to expect. So in the previous task that I described, the rating task, people used the 77 category preliminary model to describe 20 instruments, but I wanted for the Timbre Trait Profiles to have a very large collection of instruments to be used in musical analysis. And also I wanted the ratings to be on the 20 dimension and not that bigger primary model. So then the second rating task, 243 musicians, again, participated online. And the same strategy as before, with imagined stimuli, rating 34 large ensemble instruments on the 20 dimensions of the new model. Each participant rated about 11 instruments here. And finally, the results are the Timbre Trait Profiles. Quantitatively, what this means for an instrument is it's a set of means and standard deviations for an instrument on all 20 dimensions. So let's take a look at what that looks like. Here's an example of the timbre trait profile for the flute. I visualize the data with radar plots. So from the inside is 1 and it goes out to 7. 1 is the lowest rating that an instrument could have on a given term, indicating that the participants agreed that this didn't really apply to the timbre, whereas out towards the edge, towards 7, would be that it would maximally apply to the timbre. So you can see the points that are farther out are the ones that were deemed to describe the instrument best. And indeed, on the left side, I've shown the top 6 descriptors. I have these top 6 listed as snapshot profiles of the instrument. And so pure, clear, airy, breathy, and soft singing were among the top. And you can see them kind of popping out in the radar plot there. And this is just a quick slide with a bunch of the profiles that I picked that look kind of different so you can get a visual impression. I do have these slides available, and I think they're on the repository for the meeting. And so if you want to look at these a little bit further, you can check them out there, or all 34 of the instruments are, again, in my dissertation. So aside from providing these really nice little profiles, which I eventually use in musical analysis, the data from the second rating study provided really important information that I could use to assess the 20-dimensional model. The first thing I asked is, well, do I actually want to make this? Can I make this any more parsimonious? Should it be reduced to fewer dimensions? So I looked at the correlation matrix of the ratings, and a priori I kind of picked 0.7 as a somewhat arbitrary cutoff for a strong correlation for which I would decide to consider collapsing the dimensions if they were correlated at an absolute value of that or stronger, but that turned out not to be the case. So 2 pairs of dimensions correlate at 0.5, at least with that data, but most of them were under 0.3. So I ended up leaving the model as it was there. I also could look at a sort of measure of reliability, because as I said, that the first reading task was on the 77 dimensions. The second reading task was on the 20 dimensions, but I could use the 77 dimension ratings to predict what I thought that the ratings on the 20-dimensional model would be. So I could compare the predicted and actual values, and I got a really nice high number, Pearson's R of 0.96. So they were really strongly correlated, suggesting that participants between these 2 experiments were still using these terms the same way, and the reduced model was a good representation of the 77. And these were with different participant pools, although they may have overlapped slightly because of my recruitment methods. Just a quick peek of what is also included, again, in the dissertation. I've got the full profiles. I'm happy to share raw data or the CSV with the timbre trait profiles on request. I have these kind of top 6 descriptors for every one of the instruments. I have a list of top descriptors by instrument, of top instruments by descriptor, and a nice comparison of my results with those of Wallmark in his corpus study of orchestration treatises. Also a nice little hierarchical clustering model based on the semantic ratings. Okay, last part here. One obvious caveat of the timbre trait profiles, you might be sitting there thinking, but no instrument has just one timbre. We all know that instruments have universes of timbres, and the timbre trait profile is based on this idea of an instrument's prototypical sound. So there obviously is variation. And I took a first step towards addressing that, which will be, I think, important in talking about applying this to musical analysis. And doing kind of all of the things that there could be variation in timbre, register, pitch, articulation, dynamics, school of playing, instrument brand, you read that morning, different players have different timbres. So all the variation is really a lot of work, and I'm very excited that the timbre semantics group in Actor has the resources and the collaboration that we are moving ahead in that. So my little study here in my dissertation is just a step in the direction. And so I knew that I had to really narrow the scope. I picked 2 instruments, oboe and French horn, and I varied 2 parameters, which were pitch and intensity. I had 47 OSU undergrad students, and the study was again done on Qualtrics, this time from the lab because they were listening to recorded stimuli. This time I had the headphones in the lab. So they were the stimuli were recorded for the purposes of the project. They were about 2 seconds long. I represented 4 different kind of registers, 3 pitches per register, and 3 dynamics. So as an instrumentalist, I'm like very keenly aware of how much timbre can vary even between chromatically neighboring pitches. So I was really hesitant to represent register with just one single pitch. Obviously that ends up making the experiment longer, but I wanted to see how much idiosyncrasies, how many there would kind of be. And methodologically, each of the stimuli were rated on the 20 dimensions of the model that I've been describing. So to examine the results, I calculated for each of the 3 chromatically neighboring notes within a register an average value. So that represented that register. And that's what you'll see in the following graphs. But I did notice that there were these idiosyncrasies that I was thinking that there might be. And oftentimes, well, I don't know if oftentimes, but sometimes there's so much variation that between chromatically neighboring pitches might even be more different than between registers or between dynamics. But there were general trends. And some of these were linear, some of these were more like U or V shaped. And ultimately, though, it was kind of complicated. Some of the dimensions, if you remember from me reading them off, already kind of implicate pitch or dynamic, like shrill, noisy, and rumbling low, for example. So typically, often research pulls pitch and dynamics apart. My model doesn't thoroughly do that. It let the participants guide that, and they seemed to talk about these things kind of in conjunction. So those are the kinds of dimensions that tended to produce the most regular results, as you might expect. Just a very quick sampling of what some of the results looked like. So this is the airy breathy dimension for the horn and the oboe. On the x-axis, I have 4 registers. I just call them low, middle 1, middle 2, and high. And the rating is on the y-axis. So you can see with the horn, there's actually really not that much variation, and it's not necessarily as predictable. It's a little different at each dynamic level. But it's a much clearer trend for the oboe. Not only can we see that the pianissimo dynamic is in general airier and breathier, but that at mezzo, the mezzo dynamic level and the softest dynamic level, there's a trend upward with register, but at fortissimo, it sort of hits the ceiling. And I found this to be very interesting because just as an oboe player, a lot of these little graphs did kind of resound with my experiences of playing and what it sort of feels like to play. So here's a second dimension. It's raspy grainy. And in this case, the horn is much more interesting than the oboe. The oboe is a little all over the place, not very variable. But there's this clear trend for the most part that as pitch increases, raspy graininess is decreasing. And this is the same exact data, but it's plotted now with dynamic on the bottom on the x-axis, and then the color and the shape are the different registers. So you can also see that as loudness is increasing, for the most part, the raspy graininess is also increasing in the horn. And again, like there's not that much with the oboe. So just to kind of wrap things up here, this experiment also gave me an opportunity to assess my model and to compare, in this case, the ratings from the imagined prototypical sounds to the instantiated recorded sounds. So looking just at the correlation for the oboe, it was really strong. Pearson's R was 0.92. For the French horn, it was moderate but positive, and obviously, you know, a good correlation there. But there's a really big difference between the horn and the oboe, which I think is interesting, and I think has to do with the timbral variability of the horn based on pitch and dynamic, which is something the oboe doesn't necessarily have. So in imagining a prototypical sound, I think the range of sounds that were produced for the purposes of this experiment for the oboe were a lot closer to a prototypical sound than the range of sounds that were produced for the horn, because we got you can imagine like a really, really loud low horn sound or a really, really soft high horn sound are pretty far from what I would imagine a prototypical sound would be like. So I think that's part of it, but I have some other ideas as well. And just a second interesting point was for both instruments, the tendency was for participants to make lower ratings for the recorded sounds than for the imagined sounds. And I think some of the contributing factors have to do with the recording setup, as well as there may have been some kind of information and background knowledge participants that were influential on their judgments in the imagined sounds that maybe when they were presented with the actual recording sound weren't as influential. So I'm thinking if you're rating the French horn sort of generally on, or let's say with the oboe on soft singingness, it's an instrument that plays a lot of soft singing melodies, so you might be more apt to rate it more highly in that case. So a quick summary, I reviewed a set of studies from my dissertation relating to the development and application of the 20-dimensional model. I described the model building process and the study used to generate the Timbre Trait Profiles, and then the initial work into seeing how these linguistic attributes of timbre are varying with pitch and dynamic. And then I also showed how I used the data from the second two studies to assess the reliability, consistency of the model itself. So suggesting a high degree of reliability for the model in relation to imagined or prototypical sounds, and a moderate to strong agreement between the imagined and recorded sounds. So thank you so much for listening. Please feel free to get in touch. And I don't know if we have a couple of minutes for questions, but I'm happy to answer any if you do. Thank you.
We do have some time for questions. If you want to ask a question, please in the chat send a message to me that says question, and then I will take them in order. No questions yet, so I'll ask one. Oh, there's one from Yuval. Okay, Yuval.
Just really quick, I'm just curious, what were the two attributes that you found had that slightly higher correlation than the rest?
Yes.
You were talking, yeah.
No, go ahead. Can you clarify?
Yeah, when you were talking about trying to see if the 20 dimensions could be reduced, if you could collapse anything, one of the couples had a 0.5 or something, if you remember. I'm just curious.
Yeah, oh, what were they? They were both positive correlations, and both of them involved soft singing, I believe. And let me just... Hold on. There. Wait. Oh no, come back. I think one of them was negative. I think it was soft singing and percussive were negatively correlated. And then it might have also been sustained even, and it's either sustained even in percussive or sustained even in soft singing. So they were things that you would probably expect would be correlated. Yeah.
Okay, I have two more questions, one from Matt Zeller and then one from Roger Reynolds.
Let me just get my video on here. All right, there we go. Hey, Lindsey. I'm really interested in your radar plots. I thought that was really interesting. I was wondering if you could describe the positioning or the order in which the decision process of the order that you put these around, the circumference, because I would imagine that's going to certainly impact our impression of what this timbre is.
Yeah, no, it's a really good question. And right now they're just alphabetical, and I actually am not. I've had this question before, and I think there's probably a better way of doing it. And I didn't have time to kind of work through that before putting it all in the dissertation, but I may reconsider that during the article, maybe based on this correlation of matrices and the ones, if the ones that tend to be correlated are closer to each other, then we might see kind of bigger shapes happening so that they look more different from each other in some way.
Yeah, I mean, I think it's got a lot of potential. This is really cool. So
thanks.
Thumbs up.
Roger.
Yeah, really interesting presentation. I had a quick question about the 2-second duration. It seems to me that at some point it would be extremely important for you to like at least triple that with some components of your study, because I would argue that even there's a latency with our perceptual ramp up, such that the idea that 2 seconds really allows us to grasp, to scan, mentally the sample, it's just too short. I was thinking back to John Gray's work, with the 3-second E flats and so on. And I just would say that that to try what would happen to your data if the sample were at least 3 times as long would be maybe useful. Thanks.
Yeah, I think that's a very important parameter to vary as well. And I agree. And it's interesting because people will make judgments very quickly on even much, much shorter sounds. But the sound itself develops. And one of the things I found in the interviews that was important that didn't come through in the model is how people loved talking about this narrative of what happens to a sound and what the shape changes and everything. And that does get lost in this a bit, unfortunately. But yeah, that the duration, I think, will be an important thing to vary in the future. But, it's when you're planning the experiment, every extra second you have, they all add up. And I had to keep it under a half hour for my undergrads. So yeah, thank you for that. I appreciate it.
2 last questions, one from Russell Morteza and then Malta Kobe. And Lindsey, can you stop sharing? And Matt, can you get set up while these 2 questions are coming in?
Hi, very interesting stuff. I just wanted to ask a question about the dimension-based rating. So were the users or the participants tasked with, rating the sound which they imagined like a 1 or 0? For instance, the user voted that yes, this sound is pure, or that it is not pure, or that maybe you find it worthwhile to apply a scale-based rating, meaning that every single one of those dimensions is, for instance, rated on a scale of 1 to 5, because that might allow you to calculate the standard deviation across all those different dimensions, which might give a better picture. So I just wanted to, know your thoughts about that.
No, so they were all rated on a scale of 1 to 7. So when you see the radar plots, those actually reflect the numerical average of the rating. And I do have, I consider the profile to include the standard deviation because I do think that is very important.
Okay, so it was from 1 to 7 for each dimension.
Yeah,
okay.
I should have been more explicit about that, yeah.
No, I probably didn't pay attention. Okay, thanks.
Yeah, you're welcome.
Malta.
Yeah, hello. I'm sorry for being late, and I also have a parent meeting, so I hope that I can get most of the presentations today. Thank you very much, Lindsey. That's an amazing study. I have just a question. It might coincide with what Marta might think, is how did you record the instruments, and to what extent do you think that the room impact and the direction of recording might have an influence on your results?
Right, and that's one of the main reasons that the first 2 studies I had the imagined, because everything I thought of as like every little thing that you vary brings you away from the prototype. So then when I did do the recordings for the third study, they were in a room that was designed to do recordings. However, I would not have, I think they were a little close mic'd. I think especially for the horn that a lot of the kind of resonance and beauty of the sound maybe got lost a little bit. And I think that has to do with why the ratings of the recorded sounds tended to be lower, because a lot of the very positive qualities were kind of ranked lower. And I think that does have to do with the recording setup. Because people imagining a prototype are probably imagining if they're in a hall and they hear a beautiful sound. Yeah.
Sure. I just recommend that probably we have a chat about that, because that's in the center of our studies, the radiation characteristics and timbre changes with directivity. So I'm looking forward. Thanks.
Great. Thank you.
So thank you very much, Lindsey. And